So on this next page, we're going to start by reviewing some notations for the derivative. We've already talked about the derivative of functions represented with function notation as being f prime, or whatever the name of the function is, primed. If we have a function in terms of y, then we can say the derivative is y prime. More commonly, though, we're going to see dy dx as the derivative when we have our function in terms of y. And of course, this means the instantaneous change in y over the instantaneous change in x. And it's a more descriptive way of talking about what the derivative actually is, that rate of change or that slope at an instant, right? This is read the derivative of y with respect to x. And we're basically saying here is we're looking at the change in y with respect to the independent variable x here, right? We can also talk about the derivative as df dx if we are looking at a function with function notation that we're calling f. Right here, this would be the change in f with respect to x, or the instantaneous change in our function values with respect to x. Another way that we can see the derivative is that d dx of f. And basically what that d dx is noting is the instantaneous change in something, really could be anything, with respect to x, right? When we see this d dx notation, really what it means is take the derivative of what comes next. So if we're looking at d dx of x squared, we can say that what this is asking us to do is to take the derivative of x squared, and that will give us the derivative 2x, right? So right here, we've already talked a little bit about a power rule for functions that are more basic power functions, right, where we have x raised to some simple power. What we want to remember is that anytime we have our function as x raised to some constant power, we can always take the derivative with the power rule. So if we have x to the 562nd power, we can take the derivative with the power rule by multiplying in front by that 562, and then right here subtracting one of the exponents so that we've got x to the 561, right? If we have x to the pi is a constant, right? So this function we can take the derivative of with the power rule, right? So right here we would multiply in front by our power of pi and subtract one of the exponent, which would give us pi minus 1 is the exponent, right? If we have e to the e plus 4, we take the derivative with the power rule, and we would multiply in front by that e plus 4, and then we would subtract one of the exponent, giving us x to the e plus 3, right? Now we can extend this idea of any function that we can represent as x to some power, being a function we can take the derivative of with the power rule. When we look at functions like 1 over x and the square root of x. Our first example here we can take the derivative of pretty easily. X to the 5th power we would say would be 5x to the 4th, right? Right here with 1 over x, we can say that we can represent this function as x to the negative 1, right? X has a power of 1 in the denominator, and when we bring it up to the numerator, we make that power negative, right? What we're really looking at is dividing 1x, or unmultiplying 1x, with that property of exponents. And so right here, because we can represent our function as x to the negative 1, we can take the derivative with a power rule, right? And so right here, taking the derivative with a power rule, we would multiply in front by that power, and then we would subtract one of the exponent, and when I subtract 1 from a negative 1, I get negative 2, right? Now, this is the derivative, but it's not really in a usable form. If I gave you this equation and asked you to give me the slope of our original function at an x value, let's say 1, it wouldn't really be easy to do with that negative 2 power. So what we want to do is always have our derivatives in the end be in a usable form, right? And what I mean here is if we have a negative exponent, we want to write that in terms of a function with a positive exponent. So right here, I'm going to rewrite my dy dx as negative 1 divided by x squared, so that now I have a usable form of the derivative, right? Right here, when we're looking at our next example, y equals the square root of x. With that square root of x, we can represent that function as x to the 1/2 power, right? Since that square root is the 1/2 power. Now again, we can take the derivative with the power rule, right? right here, when we take the derivative of x to the 1/2, we would say we multiply in front by that 1/2 and subtract 1 in the exponent. When we subtract 1 from 1/2, we get negative 1/2, right? And again, this is not quite in a usable form. So what we're going to do is we're going to take care of that negative fraction exponent. First, we'll take care of the negative, and we write this as 1/2 times 1 over x to the 1/2. And then right here, I'm going to do two things at once. I'm going to multiply my two fractions, and I'm going to change that 1/2 exponent to a square root. So right here we have dy dx as 1 over 2 square root of x. Now, you may even remember this derivative and this derivative as derivatives that you actually found by looking at these functions with the limit definition of the derivative. And right here what we're basically saying is, look, you can come to these derivatives much faster by using the power rule, right? So right here, one thing we're going to say before we move on is, in general, we want to have our derivatives in a usable form. So what that means is that after we take the derivative, we want to make sure that when we are simplifying our derivative, we're not going to see any negative exponents or any fraction exponents, right? Now, in our derivatives, we might not do all our multiplication out, we might not do all our division out, but we always want to have our derivatives in a usable form, meaning we want to be able to plug in an x value and get out a derivative value, right? The next thing we're going to say about the power rule is that we can use it in conjunction with multiplication. One of the rules that we can talk about with regards to the derivative is that if we have a constant times a function, then the derivative of a constant times a function is going to be the constant times the derivative of the function. And right here we've got a proof of that with limit notation. Right here, if we take our constant times f of x and plug it into the limit definition of the derivative, we can factor that constant away from both terms in the numerator and even factor it out of the fraction. And then we know that that limit, and here we've got an extra limit, and right here we can distribute that limit through the multiplication of a constant, right? So right here we are left with the constant times the limit as h goes to 0 of f of x plus h minus f of x over h, which we know is our f prime of x. So we've got the constant times the derivative of the function there. Now right here what that means with the power rule is that basically when we've got something like 5 times x squared, we can say that the derivative is going to be the constant 5 times the derivative of x squared, which would be 2x. Now right here when we simplify this, we can pretty easily say that our derivative is going to basically be 5 times 2x or 10x, right? And so really when we're using the power rule, if we have a coefficient, what we're going to do is just multiply our power and the coefficient all in one step, right? So right here, if we have y equals 4x to the 6, when we take the derivative, we would just say 6 times 4 is 24, x to the, and then we subtract 1 in the exponent, and we get a power of 5, right? And there's our derivative. Now, pretty quick work, right? If we were thinking about the limit definition of the derivative, obviously we'd be doing much more work here. But right here we can basically just say, hey, look, if there's a coefficient, we're just going to multiply the power and the coefficient, and we take the derivative with the power rule, subtract 1 in the exponent, and there we have our derivative. In general, right here, when we're looking at any constant, we can say the derivative of a constant is always going to be 0. And we can look at this in two ways. We can basically say if we've got some function y equals 4, right? That's going to be a function that is graphically the horizontal line y equals 4, right? And for this horizontal line, we can say that the slope is always 0. So graphically, we can intuitively say that at every x value on our line, the change in y with respect to x is going to be 0, right? Since we've got a slope of 0 everywhere on this line, right? Now, we can also take the derivative of a constant with the power rule. So I could say y equals 4 is actually y equals 4x to the 0, since x to the 0 is 1. Now, when I take the derivative with the power rule here, I have dy dx as right here 0 times 4x to the negative 1. But since I'm multiplying 0, that again is going to give me that derivative of 0. So in general, when we think about taking the derivative of a constant, we would say that the derivative of a constant is always 0, right? So right here with our next rule, we are going to look at the idea of taking the derivative of a sum and a difference, right? And on your test, you proved that the derivative of the sum of two x expressions is going to be the sum of derivatives, right? And we can basically say the same thing with the difference with all the same steps. So right here, if we have a function as f of x minus g of x, we can say that the derivative of that function, or dy dx, is going to be f prime of x minus g prime of x, right? And really what this allows us to do, if we have something like a polynomial, or basically any series of terms raised to powers, is basically go through and take the derivative of each of those terms with the power rule term by term. So right here, if I'm looking at my first function, f of x, I can take the derivative here by basically just going term by term and using the power rule to take the derivative of each term. So right here, I would say that the derivative of x to the fourth minus 2x squared plus 2 would be the derivative of x to the fourth, or 4x cubed, minus the derivative of 2x squared, or minus 4x, and then plus the derivative of 2, which we know is 0. So we can write plus 0, but in the end, we wouldn't even write the plus 0. We would just say that that term goes away when we take the derivative, because the derivative of a constant is always going to be 0. All right, guys, why don't you go ahead and take a look at b on your own, see if you can take the derivative of that. We'll pause the video. Actually, why don't we do c and c? Right here, the d dx notation for x squared plus 3x means take the derivative of this expression. So you guys can go ahead and try b and c, and we'll come together and look at d in a second, and then we'll give you some problems that are more involved in terms of taking the derivative with the power rule term by term, like d, after we go through b and c and look at d together. All right, so let's pause the video here, and we will come back and take a look at these two in a second. So right here, as you noticed probably as soon as you started working on this is pretty light work. Right here, taking the derivative with the power rule term by term makes our calculus much, much easier. Right here, looking at the derivative of the first term, we would say multiply in front by 3, and we've got a multiplication of 3 and a division of 3 canceling out, which gives us 2x squared as the derivative of 2/3 x cubed. The derivative of our next term, 6x squared, is going to be 12x. The derivative of our 2x is just going to be 2, and the derivative of our constant 16 is going to be 0, so we wouldn't even write that. Now with our d dx of x squared plus 3x, basically again that d dx is just saying take the derivative of whatever statement comes after this. So right here we can say our change in x squared plus 3x with respect to x would be given to us by the equation 2x plus 3, where we took the derivative of x squared as 2x and the derivative of 3x as 3, right? So right here we're going to go ahead and take a look at d. Now, d is a problem that we can definitely take the derivative of term by term with the power rule, but we're going to have to do a little bit of work to represent each of these terms as x to some power, or a constant times x to some power, so that we can take the derivative of each of these terms with the power rule separately. So right here, before we take the derivative, we're going to go through and rewrite each of these terms so that we can take the derivative with the power rule. This first term, x to the 6th divided by 3, we're going to rewrite as 1/3 x to the 6th, right? And right here now we've got a constant times x to some power, so we can just take the derivative of the power rule. Our next term we're going to write as 4x to the negative 3. Now again, right here we've got constant times x to some power. We can again just take the derivative of the power. Right here, our last term, 6 times the cubed root of x to the 4th, we can rewrite as 6x to the 4/3, right? And now when we go through and take the derivative term by term, we can basically say we're just multiplying in front by that power and subtracting 1 in the exponent. 6 times 1/3 is going to be 2x to the 5th, and then right here, negative 3 times a negative 4 is going to be plus 12x, and then we'll say to the negative 4. Then right here we can say we have our 4/3 times 6, and that's going to give us 4 times 6 as 24 divided by 3 would be 8. And then right here we have x. And now when we're looking at this exponent right here, I want to talk a little bit about this, because there's a shortcut strategy we can use whenever we're taking the derivative with the power rule and we have a fraction exponent. So right here, if we were to think about the process of this, we would basically have 4/3 times 6x to the 4/3 minus 1. This is what we're doing when we're taking the derivative with the power. We multiply in front by the power, and we subtract our 1 in the exponent. Now right here we can say that subtraction of 1 we can write as 4/3 minus 3/3. So right here, basically what we've done is converted 1 to 3/3 so that we can combine fractions with common denominators. Now right here when we do that, what we're really going to be doing is subtracting the quantity of 3 away from the quantity of 4 to give us 8x to the 1/3, right, as the derivative of that 6x to the 4/3. Really what we've done here, when we took 1 and represented it as 3/3, is gotten ourselves to a place where we can subtract basically a quantity of the denominator away from the numerator, right? So a shortcut to this is always going to be basically multiply in front by that fraction exponent, and then subtract the quantity of the denominator away from the numerator, and that's going to give us our exponent for our derivative. So right here, what I would say, instead of going through this whole process, is basically I've got 4/3 times 6, right? That's going to give me 8. And then I'm going to subtract the quantity of the denominator, 3, away from the numerator, 4, and that's going to give me basically my 1/3 power that I would have when I take the derivative with the power. Now again, right here, we want our derivative to be in a usable form. So our last step is basically going to be to rewrite all the terms that have negative exponents and fraction exponents to basically take care of those negative exponents and fraction exponents. So right here we're going to have 2x to the 5th, and then right here we can say plus 12 over x to the 4th, and then right here we can say plus 8, and now right here that 1/3 power is going to be the cube root of x. And now we have our derivative in a usable form where we can basically plug in an x value into all 3 of our terms and get numbers that we can then combine to give us a slope value for our function f of x. All right, so right here on this next page, you guys are going to try some of these on your own. I'm going to give you these 2 to try on your own, and then we're going to talk about the last one together. So why don't you guys go ahead and pause the video here, and we'll come together and look at this in a second. All right, so right here, looking at these 2 guys, we have to first rewrite our functions so that we can take the derivative with the power rule term by term. So for our 5x to the 4th minus 1 over 2x squared plus 2 divided by x to the 7th, we're going to bring those x terms up into the numerator, and right here we'll have 5x to the 4th minus 1/2 x to the negative 2 plus 2x to the negative 7. We then take the derivative with the power rule, right? And we get 20x cubed plus x to the negative 3 minus 14x to the negative 8. And then, of course, we have to take care of negative exponents. So right here, we'll bring these x's with the negative exponents back into the denominator, and we get 20x cubed plus 1 over x cubed minus 14 over x to the 8. For our b, we again have to take care of that second term and rewrite it as a constant times x to some power so that we can take the derivative with the power rule. Right here we can say that our x squared plus 6 over the cube root of x can be written as x squared plus 6x to the negative 1/3. We then multiply in front by the powers and subtract 1 from the exponents from both of our terms, and we get 2x minus 2x to the negative 4/3, right? And then, of course, that second term has not only a negative exponent, but a negative fraction exponent. So basically right here, what we would do with that second term is bring that x into the denominator and change that to the cube root of x to the 4th in the denominator for that second term.